equilateral triangle with side length 12. A. Show that each angle bisector of an equilateral triangle is also a median. B. Find the length of an in-radius of triangle PQR.
Okay. Let's jump to that solution. Can you please read that for us?
Let line PL and line RN be bisectors of triangle PQR. Since the angle bisectors of an equilateral triangle are also the medians of a triangle L, the midpoint of line RQ, and the incenter I is also the centroid. So I divides median line PL such that PI over IL equals 2 over 1. Therefore, IL equals PL over 3. Triangle PLR is a 30, 60, 90 triangle. So RL equals PR over 2 equals 6. And PL equals RL square root 3 equals 6 square root 3. Finally, we have IL equals PL over 3 and 2 square root 3. Note, we can also have solved this problem by noting that triangle IRL is a 30, 60, 90 triangle. Instead of connecting the midpoints to the opposite vertices, suppose we connect them to each other, as shown in figure 7.3. Triangle DEF is called the medial triangle of triangle ABC.
There you go. Okay, oh my goodness. So there you have all sorts of wonderful relationships, taking on what we've already learned about the in circle. We have an in radius, okay, that gives us an in radius. We also have a 30, 60, 90 triangle if we are bisecting the equilateral triangle. And then we get a medial triangle, another terminology, hooray. Okay, so we just learned two very important properties, okay, of well, we can call these medians or joining median points. We get a medial triangle. All right, thanks, Quartz. That was awesome. Altitudes. We've already seen altitudes. All right, let's see what we're going to learn here. Let's take a look. We have Sophia. Can you read for us the 7.5 altitudes? And then you're going to read problem 7.22.
We already seen altitudes in our investigation of triangle area. You can probably guess by now that we'll prove first about altitudes.
Thank you. Carry on.
In this problem, we will prove that the lines containing the altitudes of any triangle are congruent. This is a pretty slick proof before trying it. You might want to review that we learned about the medial triangle in section 7.4 here.
Okay. Okay, you want to read A for us, please?
A, our diagram shows altitudes A, D, B, E, and CF of triangle ABC. Draw a line through A parallel to BC, a line through B parallel to AC, and a line through C parallel to AB. The intersections of these three lines form another triangle. Call this triangle JKL, with A on KL and B on JL.
Okay, so then we, after doing that, I'm going to jump to the solution. They're going to show us that triangle CAK is congruent to ACB. Let's take a look. Oh my goodness. So you drew a line, KL. We're looking at this diagram here. Okay, this was our original triangle ABC. And then if we draw a line parallel to CB, another line parallel to AC, another line parallel to AB, you get a bigger triangle, and they're calling that JKL. All those exterior triangles are actually congruent. Interesting. Well, to prove it, that's another thing altogether. So how about, Sophia, you read the important for us, please.
The altitudes of any triangle are congruent at a point,
Concurrent.
at a point called the orthocenter. We usually denote the orthocenter with the letter H.
Mhm. Okay, so to get a good feel for the orthocenter, we look for it in a few different types of triangles. Okay, let's take a look here. What is the orthocenter? So you take a look at what would our orthocenter be here? They call it H, but you take a look at all the altitudes, not necessarily the medians this time. So instead of being called the centroid, it's now called the orthocenter. Okay, so it does not label, but this center right here, I'm showing it. I can't pinpoint unless I import it into my whiteboard. Does everybody understand what orthocenter means?